So let's re-emphasize some of the points of what are used as drivers for these integrated assessment models to produce the SSPs. Right? The population projection is always interesting and problematic. So here we have projections or history from, oops, what did I do? 1960 onwards, and then projections done at that time. So you have various pathways in which the population itself will grow and education. So this is literate share used for SSP marker scenarios, percentage of population that is literate. So different SSP 1, 2, 3, 4, 5 have different ways in which populations are treated in the evolution through the 21st century, and there is a corresponding growth in populations in millions. And you can see that here the literate population is lower and population is higher, whereas there is a turning around of after peak population in some of these scenarios, which are kind of a strange combination of literate population dropping but populations also dropping. Okay, percentage of global urban population, again historic and where we are going. So there are various details here which I'm not going to talk about. You can follow up on the paper. Basically these are assumptions, so you can imagine that there are obviously all kinds of assumptions made in making future trajectories of population, especially whether population projections are including what's basically happening already in terms of women with higher education and larger income having fewer kids, and consumption still goes up. So reduced population doesn't necessarily come with reduced consumption, which can be a tricky assumption in the models. Okay. In the meantime, trillions pegged the GDP in trillions of US dollars pegged to 2005. You can see different SSP markers compared to other literature studies. So literature studies are shown there, and what this community developed as for the marker scenarios. Various ranges are given here, again details, but just note that the range is fairly large by 2100 with very low global GDP to very high, and again fossil fueled pathway can take us to very high GDP, but then comes with lots of other problems, right? Low complexity, low challenges to adaptation, but high challenges to mitigation. If you keep on burning fossil fuels, and you have to keep on taking out that CO2 and hide it somewhere and so on and so forth, or even reduce the emissions in the first place with EVs, renewables, well, not renewables because you have fossil fueled growth of GDP. Okay, so GDP per capita and the Gini index is kind of a purchasing power kind of index that's commonly used by economists. You can look it up. I've discussed it elsewhere. So again, we're going from historic period into the projection period. The range of GDP per capita, thousands of US dollars pegged to 2005, is also very low in some scenarios. These are marker and non-marker ranges, so the colors are ranges, and you can see per capita GDP can be high, but it may come with lots of fossil fuel use, including coal, whereas here you have low per capita GDP. So these don't necessarily tell you standard of living versus quality of life, right? So if you have very clean air, clean water, and good transportation, etc., will the quality of life be high, even if standard of living is not by that standard high, some standard. Okay, so looking here at development of global population and education, urbanization, GDP and GDP per capita, and the Gini index, the inset panel A, so we already looked at these. gives the share of people without education at age of greater than 15 years. And the instead of panel D denotes the development of the global or cross-national Gini index. SSPs are compared to ranges from other major studies in the literature, and so there are some details here. So you can see that SSP1 has lots of scenarios and range from SSPs and the marker scenarios. So for SSP1 you have here, so the colors here obviously indicate GDP as seen here, and a range of alternative SSP GDP projections are presented in this special issue. This particular journal issue was a special issue which discussed various aspects. I've taken just the overview paper. So there are other major studies. We looked at IPCC SRES scenarios 8C before, AR5 working group 3 scenarios, interquartile range 100% and with the full range, Gruber et al. Range, UN urbanization trend to 2050. So you can see there are different projections that we looked at here from different sources. Okay, so there's a mix and match. So primary energy structure here and final energy demand shown here of the SSP marker scenarios and corresponding ranges. These have serious implications, of course, in terms of land use, competition between food, water, and energy, and emissions, of course. So primary energy structure 5 marker scenarios from SSP1 and then mix and match to models. Not every model does it. So SSP1 done with image. So you have coal, oil and gas and non-fossil going out to 2100. So you can see non-fossil increases, oil and gas decrease, and coal decrease, but they don't disappear. In SSP2 you have different combinations done with a different model here. Okay, similar, the scales are normalized here, so you have to be just careful. SSP3, SSP4 and SSP5. So is there a problem using different models? Well, presumably, because consistency between the pathways and emissions need not be guaranteed in this case, as we described when we discussed the RCPs. Primary energy triangle, putting together all IAM scenarios. So you're going from coal to renewables here and then to oil plus gas over there. So you end up with different regions being occupied as a combination of all three in different scenarios. So if you look at SSP1, you are here with some combination of renewables and oil and gas and coal, and the legend A here, so we can look at non-fossil, renewable, nuclear, oil and gas. In B we are looking at what we looked at before, and this is what the history shows from 1850 to 2010 in terms of how coal has done, how it has become uneconomical to burn coal. Renewables have increased, nuclear has increased, and so on and so forth. Okay, total final energy demand combining all IAM scenarios, we looked at this before. So here you have AR5 scenarios and SSPs up here, various ranges as well by 2100. In SSP1, for example, you are beginning to drop off after peaking around 2050. Basically, SSP1 has to meet the less than 2 degrees C goal, is promised to meet it, so which means oil, coal, etc. have to be left in the ground, assets left buried in the ground, as the oil people talk about it, and so on. Okay, croplands, another key feature, especially since reliance on bioenergy is very high in some of these scenarios to meet the most sustainable of the pathways. So we are looking at millions of hectares in terms of cropland, where the AR5 scenarios were in terms of their maximum and minimum, where the various RCPs where and where the SSPs fit into that as well. So this is divided into pasture, so scales are different, be careful. Forests, so RCP 4.5 increases in the AR5 matchup by 2040. Is it happening? Well, you have to watch out. So here we are, lots of losses in the AR5 minimum scenario, and AR5 max is somewhere here. Okay, this is AR5 max, this is RCP 4.5. So what do you do with this? Just keep in mind that as we go into the future, there are large ranges in each of these, which translates to large ranges in emissions and challenges to adaptation and mitigation, with large uncertainties. And again, along the way, as emissions increase or decrease, the climate change response also changes. So the uncertainties in climate response itself is kind of clubbed into these probabilities of future warming, etc. Other natural lands, RCP6 would take us there, 4.5 and so on. So this is useful. What are the implications? You can read the paper, and then there has been subsequent literature by various social scientists arguing that assumptions of bioenergy in SSPs is basically unrealistic in terms of not considering the competition with food production, food security issues, water security issues, and just in terms of meeting the goals of bioenergy and the area of land it will need if we really have to reach the goals. That's why some models cannot necessarily accomplish the 2°C warming scenario in their models, because the model framework does not convert the bioenergy into those kind of temperature targets. Okay, looking at greenhouse gas emissions for CO2 and non-CO2, so methane and N2O, etc. Again, comparing to AR5 scenario max, you had in AR5 it would have been RCP 8.5, which is here, but max was there and min was here, so it did have negative emissions starting around 2060 in terms of CO2. 2.6 reaches 0 and goes slightly negative by 2080. 4.5 goes here. As we talked about, RCP 4.5 can be higher than 6.5 in early years because of various ways in which things evolve, but you can see the range here as well. Okay, this is for methane numbers. Again, these are in millions of tons, these are in gigatons, and these are again in millions of tons, so you have to be careful. So they, we have to always compare concentrations but also residence time. Methane remains in the atmosphere for about a decade, but it's 25 times as powerful as CO2 as a greenhouse gas. N2O remains for a couple of centuries, and it's over 200 times as powerful a greenhouse gas as CO2. But how this comparison is computed is also debated, but we will not go there. Okay, looking at aerosol and air pollutant emissions, so short-lived climate pollutants, which actually can have an advantage if you mitigate them, as we talked about in the course Bending the Curve and elsewhere. They can give you maybe temporary increase in global warming rates because sulfate aerosols can be cooling. Black carbon is warming, but health effects, co-benefits, and eventual peak management will work better, but nonetheless they have to be removed because they are pollutants, right? So they are sulfur, AR5 min and max, with various RCPs fitting in between and SSPs going along with those. So that's black carbon and radiative forcing associated with those. So here is where you begin to combine SSPs and RCPs. So you can see here is RCP6 with SSP1 going there, and RCP 2.6 coming in here, and so on. So consistency between emissions, socioeconomic narratives, and climate responses are all a deadly combination, and they are dealt with by giving you uncertainties in various forms. Looking at the summary of shared shared climate policy assumptions, or SPAs, for mitigation, shared climate policy assumptions. All SPAs foresee a period with moderate and regionally fragmented action until 2020, which we're already way past. We're in 2023 as I'm recording this, but differ in the development of mitigation policies thereafter. Mitigation policies, you can look at what is being implemented in terms of renewables and EVs, for example, with some haphazard attempts at reforestation, afforestation under the nationally determined contributions, right? Policy stringency in the near term and time of regional participation. So SSP 1, 4, 2 and 5 and 3. Early accession with global collaboration as of 2020. This is before 2020, so remember that. Some delays in establishing global action with regional transitioning to global cooperation between 2020 and 2040. Late accession, higher income regions join global regime between 2020 and 2040, while lower income regions follow between 2030 and 2050. So coverage of land use emissions is done in various scenarios here. 1 and 5, effective coverage at the level of emissions control in the energy and industrial sectors. In SSP 2 and 4, intermediately effective coverage, limited red, reduction in emissions from deforestation and forest degradation, but effective coverage of agricultural emissions. Here SSP 3, very limited coverage, implementation failures and high transaction costs. I won't go into the details further here. Primary energy intensity improvement rates, again various assumptions with baseline scenarios and various RCPs translating into various SSPs. So are they all consistent with each other? Well, 2-degree emission scenarios below 1.5 is not even shown here, but some people are sneaking just around there. So where we need to be 2010 to 2100. So annual long-term improvement rates of energy intensity, so final energy per GDP, and carbon intensity, which is CO2 per final energy. Development in the SSP baseline and mitigation scenarios are compared to the scenarios consistent with a likely chance to stay below 2 degrees C from the IPCC AR5. This is the shaded region. Large icons and colored lines denote the SSP marker and associated mitigation scenarios. So SSP 3 goes here, SSP 5 comes down here, and SSP 1, the most benign one, stays down here with energy intensity and carbon intensity both being low, right? Smaller icons denote non-marker IM interpretations of the SSPs, so you can see different markers here. I think I should hurry up on this. This is upscaling of low carbon energy forest expansion in CCS, because we are looking at major mitigation options in the energy and land use sector. Upscaling of low carbon energy by 2050, expansion of forest land cover by 2050, and contribution of cumulative carbon capture and sequestration over the course of the century. This is really relying on a technological promise that still doesn't exist in terms of the scale of carbon drawdown and the amplitude, the gigatons that can be drawn down. Nonetheless, look at the various scenarios of how low carbon energy has to be scaled up by 2050. SSP 1 and SSP 4 are here. SSP 5 is down here because it's going to keep burning fossil fuels, as you remember. Mitigation scenarios, obviously 2.6 will require lots of mitigation to meet the targets we talked about here. If you go to RCP 6, the mitigation challenges are low. This is where we talk about mitigation versus adaptation challenges. Look at that. Change in forest land cover 2010 to 2050 in millions of hectares. SSP 1 range is here between positive and negative, but loss of forests is pretty much guaranteed in these, and SSP 5 stays here. So in terms of mitigation scenarios, again 2.6 requires massive increase in land cover, which is not there in other scenarios. And CCS 2.6 relies somewhat less than 3.4 and 4.5 in the maximum, but in the minimum it's up here. So obviously, in terms of gigaton CO2 between 2010 to 2100, are these numbers achievable? We are relying on that being the case. Looking finally at the forcing level in watts per meter squared and carbon price, this is important, even though it's not an easy thing to figure out the carbon price or the social cost of carbon or how the carbon markets will actually work out. But you can see SSP 1 to SSP 5 and the baseline here, and various forcing levels and the amber diagrams or the color codes here. There are numbers here with ranges, carbon prices, and the attainability of alternative forcing targets across the SSPs. The colors of the cells are indicative of the carbon price. You can convert the price here to forcing here. To get lower forcing, to keep emissions low and meet the global warming targets, carbon price has to be high. If you don't care, then obviously you pay less for carbon, your sins, right? The numbers in the boxes denote carbon price of the marker scenario with a full range of non-marker scenarios in parentheses here. White cells indicate the position of the respective baseline scenarios. Empty cross cells could not be populated, not enough model simulations. Carbon prices are shown in terms of the net present value of the average carbon price from 2010 to 2100 using a discount rate of 5%. Discount rate is basically how fast you think a dollar today will fall in value going into the future, or how much you have to invest now to reach a certain dollar value of benefit in the future. So this is a huge complication in terms of going from 3% discount rate to 5% or 10%. Higher the discount rate, less the value of your investment in the future, so more the excuse to avoid it, for example. Mitigation costs for the other metrics, GDP losses, consumption losses, and abatement costs are provided as well in the supplementary material. Note that SSP columns are ordered according to increasing mitigation challenges, so low challenges to high challenges, so these are not in order. SSP 1, 4, 2, 3, and 5. So if you remember the narratives, the combination of mitigation is different in each of them. Okay, coming closer, let's read off the couple of paragraphs from the conclusion. Conclusion is rather long with discussion. I won't read the whole thing. You should definitely read it if you're interested. The next steps of the community scenario process will comprise collaborations with the climate modeling teams of CMIP 6, so that there were iterations, so this was already done, to assess the climate consequences of the SSPs, partly done. This work is organized as part of the scenario MIP, where MIP is Model and Comparison Project. In addition, the modeling protocol that has been developed as part of this study is made available to the IAM community in order to enable widespread population participation of additional IAM modeling teams in quantifying the SSPs. Most importantly, the SSPs and the associated scenarios aim to enable impacts, adaptation, and vulnerability researchers to explore climate impacts and adaptation requirements under a range of different socioeconomic developments and climate change projections. This is said easily, but the amount of investment needed for adaptation and the potential for maladaptation because of the uncertainties of projections. In the beginning, let's say 2 decades, the uncertainties in the projections are dominated by models, system models, but beyond that, scenario uncertainties dominate the range and projections themselves. So investing based on those is always, challenging. The plan is for an evolutionary expansion of the scenario framework matrix so that a large body of literature based on comparable assumptions can emerge. Beyond the work of the global SSPs, important extensions are either planned or underway for regional. These include extensions with respect to other sectors, specific regions, and for Europe, or increased granularity and heterogeneity, for example, with respect to income distributions or spatially downscaled information on key socioeconomic drivers. Adding details like this, does this really add more value, reduce uncertainty? Not necessarily. Sometimes increased knowledge doesn't necessarily come with reduced uncertainty. Okay, so I will leave it here, and then we'll come back and try to follow some of the other issues of IPCC interactions with governments and acceding to their demand on going from 2 degrees to 1.5 degrees, calling it an aspirational target, and doing scenarios to try to meet them, knowing very well that we are very close to overshooting it. 2023 will be an El Nino year by all predictions and indications from observations. So how El Nino will probably push us temporarily over 1.5 degrees, and when we will come back, and what the consequences will be, etc., are part of this debate. Okay, we'll talk about this elsewhere.